Next up is Rod Stucker. Rod was chosen as the winner of the Envelope Technologies campaign in our crowdsourcing 1.0 campaign, as I like to call it. Rod is an entrepreneur specializing in zero net energy design with focus on integrated design systems, architecture, and home automation. As owner of RM Enterprises, he works on the development of state-of-the-art passive house and zero net energy construction in the residential market, including the use of solar thermal, solar PV, ground source heat pumps, de-superheaters, and hydronic systems that provide radiant heating, cooling, and hot water. Rod's idea entails a novel approach to installing high-performance EPS foam window frames and insulated glass units at the job site. This would both reduce the risks of improper installation and ensure a tight, well-insulated, and therefore energy-saving window package. Rod, welcome you up to the stage. And again, I'll remind you, we are being tight on your 7 minutes.
I have asked that they allow me to do a pre-recorded PowerPoint. It's in your best interest that we do that, so we'll proceed, and then I'll be happy to answer any questions afterwards. EPS frames and high-performance insulated glass units are capable of providing an overall coefficient of heat transfer of less than 0.05. This is equivalent to greater than R20. Low-cost 40 psi and 60 psi density EPS materials with insect-resistant agents are utilized primarily for picture windows of energy-efficient homes and commercial buildings that employ adequate ventilation. Combining high-density EPS foam frames with high-performance IGUs can save up to 5 quads of energy annually in the U.S. Windows typically account for about 30 to 50% of the transmission losses through the building envelope, even if their area fraction of the envelope is far less. It is estimated that for highly insulated zero-energy structures, transmission losses through windows and doors can account for up to 90% of total energy loss. Frames comprise on average 20% of the window area. In the case of the high-density EPS frame prototype, it comprises 31% of the window area with a full 4-foot by 6-foot viewable portion of the window. As the insulating capability of frame components is increased, it can have a substantial effect on thermodynamics of the entire window package, often boosting the window's thermal resistance by 2 to 3-fold once thermodynamic equilibrium has been achieved. The current weakness of conventional windows is due primarily to poor thermal performance of frame materials, IGU spacer materials, and inset design. IGUs are typically designed in which spacers are placed about 1 inch below line of sight. Increasing the inset to 1.5 inches below line of sight will increase thermal performance of the frame, particularly at the edge of glass. Most conventional window frames are currently rated between R1 for aluminum and up to R2 for wood and vinyl materials. This substantially compromises the associated R value of the glazing system, which can be over R20 for high-performance insulated glass units. Window manufacturers can use ENERGY STAR labels to promote the performance of their windows. High-density EPS window frames and high-performance IGUs are designed and installed in order to substantially improve the U factor, air leakage, and condensation resistance. ASHRAE whole window U factor samples are used as a reference point for comparison with the high-density EPS foam window frame and high-performance glazing systems. Based on the above ASHRAE window samples, on average, the best double and triple pane windows with wood or vinyl frames and krypton gas fills are rated from about R2 to as high as R4.35. High-density EPS foam frames can provide between R6 to over R11 for double and triple pane windows. Preliminary modeling and simulation of 4-layer high-performance windows reveal that innovative high-density EPS frames and high-performance glazing systems using krypton can economically boost thermal performance by over 3-fold, in other words, to as high as R17. The following are advantages of multiple-layer IGUs. Innovative gas filling can reduce cost of using krypton by 50%. In combination with reducing krypton gas filling, reducing costs of window frame manufacturing, and direct marketing and sales allows for substantial reducing costs for high-performance window packages. The field of material science and engineering holds much promise for the future development of high-performance window frames and glazing systems. The following is a list of thermal conductivity and emissivity of materials for production of high-performance window frames and window glazing systems. Among the most commonly used insulating materials of today are expanded polystyrene and extruded polystyrene. Of these, EPS is the most commonly used for wire cutting and molding. The relatively high performance of polystyrene foams is due to the carbon dioxide, which uses an insulating gas within each cell of the material. EPS can be produced with compressive resistances of 40 and 60 psi. Within that range, EPS can meet specific strength requirements for use in high-performance window frame materials. ASTM standards are utilized for production of rigid cellular polystyrene thermal insulation products. The following ASTM test specifications for C578 types, specifically 14 and 15, correspond to 40 psi and 60 psi respectively. EPS design considerations are included in development of high-density EPS foam frames. Compressive strength at 1% deformation for 40 and 60 psi foam appear to be more than adequate for the surface area applied at the weight-bearing edge of IGUs. The expansion and contraction of EPS foam is similar to other building materials. The following are characteristics of EPS materials. High-density EPS foam frame phototype displays using TrueLight 2 and 3-layer sample IGUs. 2x6 exterior wall with the equivalent of an R5.18 IGU and R9.24 frame. Thermal isotherms for an R6.67 dual pane window with silicon foam spacer and IGU pocket sealant. 16-inch thick ICF wall with the equivalent of an R7.35 IGU and R13 frame. Thermal isotherms for an R10 triple pane window with silicon foam spacers and 0.4-inch 20% argon, 80% krypton gap fills. Currently in development stages, vacuum insulating materials can potentially be mixed with other polymers in order to provide compressive and fractional strength required for production of thermal resistant spacer bars and IGU pocket liners for high density EPS foam frames. R7.52 window with vacuum insulated spacer and addition of 1/2-inch vacuum insulated thermal barrier for IGU pocket liner and sealant. Thermal isotherms for an R11.36 window with vacuum insulated spacers and 0.5-inch thermal barrier IGU pocket and 0.4-inch 20% argon, 80% krypton gap fills. We are interested in developing strategic partnerships in the fields of material science and engineering and business development for commercialization of the next generation of high-performance window frames, insulated glass technologies, and exterior entry doors. I wish to offer my sincere appreciation to Melissa Voss-Lapsa and William Miller of the Oak Ridge National Lab and their staff associated with the crowdsourcing campaign for this opportunity. I am also grateful for the assistance of the Lawrence Berkeley National Lab staff for their development of Windows 7.3 and Therm 7.3 software, which has been used in conducting modeling and simulation of window frames and glazing systems. Last but not least, I am extremely grateful for Gary Beamer and Josh Johnson at FMI-EPS for their assistance with developing our first generation high-density EPS window frame prototype, and Bill Evers and Steve Brisbane of TrueLight Knoxville for providing IGU samples and assisting us with the installation and transportation of our prototype displays to the Oak Ridge National Lab for the EERE Industry Days event hosted by the Oak Ridge National Lab.